Hallelujah, hallelujah. Truly he is risen. Hallelujah, hallelujah. Quite a few are missing here. I guess they're still sleeping, I would presume. Okay, so let me sort of go back to something I taught yesterday. I forgot to, probably you caught it, but I did mention it correctly, but I did not write it correctly on the notes. So just want to make sure here. So let me share. All right. So let me put this right here. Yeah, yesterday when I talked about this one here. So if you go like faster, if the object, the source, um, the object that gives us the source of light or a source of sorry, the waves, if it goes faster than the speed at which the waves travel in the medium, of course, like all the sound waves are behind, like the boat in this case. So the boat does not experience. Yesterday, I did not put this here. I said does experience in its disturbance. Of course, it does not experience any disturbance because it's already behind it. So the boat will go smooth sailing. Right. Same thing happens with jet going faster than the speed of sound, so everything is super quiet. They cannot hear like anything that comes from outside because the sound is already behind them. All right, so before I move on with this, is there any like general questions here or no? Okay, so as I promised yesterday, talked to you, like I asked you, like I told you that tomorrow I'm going to sort of look at some of resonance modes, especially regarding like musical instrument. So little review. You don't have to take those notes down. If you want, you can, but please do not put this as part of your sound ISU, right? So when you send it to me, I don't want to see this. All right. Okay. So a little review here. So remember here that waves, unlike particles, if I have a wave like coming like this, another one here coming like that, of course, when they interact, when they overlap, you have what is called the principle of superposition, right? So what happens here is that those two are still there, they're still traveling, right? But the displacement, the total displacement is made up by the algebraic summation of displacement of each, right? So here, this is like construct interference. If you have like something like this instead, right? So you would have destructive interference, right? So when those two waves, when the centers of each coincides, this would look like more like this, all right? So the displacement here is less than what it was before, okay? So that's destructive interference. So we learned about this. Now, if I have a chord, and this is a wall right here, if I have a chord and I keep on sending like pulses, all right, so those pulses will travel. And remember here, whatever wave encounters a new medium, there are three things that may happen, that will happen, that may or may not happen. One is reflection, one is absorption, and one is transmission. So some of the wave energy, of course, is transmitted into the wall, right? Not too much. Some of this transmission here will be absorbed. So it means a conversion of wave energy into some other form, so thermal energy for the most part. And you have reflection, right? So if I keep on doing this here with my cord, my flexible cord, when it gets to the wall, it's going to get reflected. So I'm going to have like a series of reflected wave that will sort of come towards me, right? So what happens here is that I have like two waves, an incoming wave and an outgoing wave, a reflected wave, and they will interfere, right? This is what interference is. Interference is the overlap of any two or more waves, right? So they will interfere. And if I sort of do this at a definite frequency, not any frequency, if I do this at definite frequency, I'm going to get a special case of interference that is called standing modes or resonant modes. So if I do it at a special frequency, what I may sort of end up with, I may end up with something that looks like that. All right. And I did a demo in class for those who were there. All right. So here, this is it's called a standing mode here, or resonant mode. All right. And so this is the lowest frequency. So once again, it's very misleading. A standing mode doesn't mean like it stands. It just means that it seems as if it's not moving. But the standing mode here is actually made up of traveling wave, these waves here, like the ingoing and the reflected one, right? You just don't see it, but that's the overall result here, right? That's the interference. This is the resultant wave from these two here, right? As a result of the principle of superposition, right? Okay, so this is called the standing mode here. And of course, if I go up and down at a frequency that is a little bit like higher, but it has to be very specific, I'm going to create like those other standing modes. So the next one I'm going to create is something like that. All right. So that's another standing mode. This is called the first resonant mode here. Right. Don't write this down. Right. First resonant mode. This is the second resonant mode. And so on and so on. So you can see here that if the length of the chord is L, and the chord is L, what I'm doing here is I'm fitting like a full, I'm fitting a full wavelength, right? A full wavelength into it. So I'm going to sort of call this like the wavelength. I'm going to put like little 2 here. Little 2 refers to the resonant mode that I'm in, right? And what you see here, you see that this is equal to L. In contrast, the first mode right here, I'm fitting actually like half a wavelength. So you remember like a point where there's no displacement is called a node. So here, this is a node, right? Whoops. This is a node right here. This is a node right here. This is a node right here. I know I understand I'm on this side here and I'm doing this, but eventually I can sort of stop moving and it's going to go on, right? So that's a node. Here I have a node right here. I have a node, right? So here you can sort of see here that from one node to another node, I have half a wavelength, right? So this is like half a wavelength from here to here. So I'm fitting, of course, so I'm fitting half a wavelength into L because it's still L, right? So the string is still L long, and I'm fitting half a wavelength into this. Now, once again, the little one here, just keep track of which resonant mode I'm at. And of course, if I figure out like the wavelength for the standing modes here, I've got, of course, twice the length of the string. And then so on and so on. Remember here, I told you that before the speed of the wave does not depend on the frequency nor the wavelength, right? It depends on the property of the medium in which the wave travels. So if it's a string, it will depend, as you may have learned, it may depend on the, if the length is fixed, it may depend on the tension. It may depend on the how much mass there is per unit length of your string. And it may depend also on the diameter of your string. All right. So you've seen this in the textbook. They give you like proportional and inversely proportional relationship that exists between the frequency and tension, mass, linear mass, and diameter. Anyway, so the speed here, so it's the same string in both cases here, like right here and right here. So both same string, same tension, same diameter. So everything is the same. except of course like the frequency with which I move this up and down. So the speed is the same in both. So as the speed is the same in both, so you have the speed in the first one is the same as the speed in the second one, and then you make use, of course, of the universal wave equation. And then so if you put like the value for the wavelength, which is twice the length of the string here and a full length here. So if you put this in, what you get this. There we go. And then you can take off L, and what you get is you get this, right? So you get that the frequency of the second resonant mode is exactly twice the frequency of the first mode, right? The first resonant mode, right? And if you continue here, you're going to see the third resonant mode. So the third resonant mode here, right? You will have like something. Whoops, sorry. Third resonant mode. So you would be fitting, instead of fitting like a full wavelength, you're going to fitting like 1.5. So 1. There you go. All right. So here, this will be like your third resonant mode. And in order to create this mode here, I would need like to go up and down at a frequency higher than the fundamental. And it will be exactly 3 times, right? So the frequency of this one here will be exactly 3 times the frequency of the first, right? Okay, so whenever the frequency of the other resonant mode is an integral multiple of the first, we say that those modes are harmonics, right? So that's another word here, harmonics. So if you want to come back, if you want to go to this, let me see here, this page here, all right? So make sure that you have this. I will try to rotate this page. Counterclockwise. There we go. So I did rotate it. Oh, you can see the whole thing on the screen. That's fine. Okay. So here, this is a summary here of the resonant mode that you can have. There's like 3 possibilities here. One possibility is when both ends are fixed. So they're called 2 closed end or 2 fixed end. And this is what happens in a guitar string. And the guitar string, it's at one hand, it's being fixed. And at the other end, you put your finger to force a note, right? In most musical instruments here, what you create, not all the time, but what you create for the most part is the first resonant mode. Of course, you create these as well. But the most important one, for the most part, will be the first resonant mode here. So as I said earlier here, so this is your first resonant mode. You're fitting half a wavelength. You have a certain frequency. The first resonant mode is called also the fundamental. And it's also called the first harmonic. And this is the number of notes, like 2 notes here. Now the second one here, you're fitting a full wavelength. And as I said earlier here, the frequency of the second will be exactly, of the second resonant mode will be exactly twice that of the first. The second resonant mode is also called the second harmonic, and it's also called the first overtone, right? So this is the third one. You're fitting like half a wavelength, sorry, 1.5 wavelength. The frequency will be 3 times that of the fundamental. This is called also the third harmonic and also the second overtone. And this is the formula here, where N is your resonant mode here, the number, right? So N is the N equal to 1 is the first, N equal to 2 is the second, and so on, right? So this is the how much you're fitting into L. And this is the formula here for the frequency of the next overtones compared to the fundamental, right? Now, to open N. So remember here, let's see here, where's that? There you go. So remember here how I did create like this standing mode. I created the standing mode by constantly sending like pulse towards a wall, and it got a reflected back. And if I do this at a special frequency called a resonant frequency, I'm going to get like those standing modes here, right? And then I can stop moving the cord up and down. This is my source, by the way, right? A wave always has a source. The source here in this case is my hand, and the frequency of the source always matches the frequency of the wave that is being created, right? Okay, so if I stop this here, I'm gonna get like something like that. And the property of standing modes, resonant modes, is that they're very long lasting, right? They pack a lot of energy. I don't have like to put like too much energy in. It's gonna sort of keep on increasing the amplitude greatly. All right, and it's gonna take a long time to die down if I don't input any energy. Of course, it's going to die down because there's loss due to thermal energy and so on. So, all right. So remember here. So this is what happened here. So I got this standing modes by making use of the fact that I have waves that are being reflected with the same frequency as the incoming wave, and then these interferes with each other to give a special resultant wave called standing modes. Now, so this is like for guitar strings, violins, piano, all the like. Now this one, I also like to have this with you, so if you can have it. Okay, so this one here is this. This is called like brass instrument, for instance, trumpets, like trombones, all of this. What you actually have here is you actually have an open end. This is where you put like your mouth. This is the mouthpiece here. So the mouthpiece is your source. So what you do here is you buzz, you make your lips like go up and down, vibrate at a definite frequency here. If you don't put your mouth here, you can put like a tuning fork if you wish. So that's the source here. So what happens here is you're going to create sound wave, and remember those sound waves are longitudinal waves, right? Not transverse wave, right? So the longitudinal wave will go down the tube, and then when it comes here, this is also open, right? This is also open. It's not closed. It is open. Now, some of the sound will come out, but not too much here. Now, for a reason which I will not explain, there's also reflection. You might say, "Oh, why? Because it's open. Why doesn't it go all the way out? Why does it reflect?" Well, anyway, so take it like as granted here, there'll be a reflection, all right? So there'll be reflection. So what happens here is that you have the same condition as for the guitar, or for the string, right? So remember, I keep on sending input waves and it keeps reflecting back. I have the same situation here. And if you buzz your lips, or if you have a frequency that is a resonant frequency, what you're going to have like those two waves, incoming and reflected waves. They will interfere in such a way as to produce a standing modes. And those standing modes, as I said earlier here, they're very, very, very strong, right? So that's why when it comes out, when some of it leaks, and also when it vibrates the surface of your instrument, it's going to be able to displace a lot of air, and then so you're going to have a very large sound amplitude. And when it impacts your eardrums, it's going to make your eardrum like moves like quite a bit, and then you're going to interpret this as sound, right, of a certain pitch, all right? So these are example of what we call open ends. So they're open on both sides, open on both sides. Now, if you go back to this one, so this is the case of two open end or two free end, all right? So trombone, trumpets, clarinets, I think, all right? So these are all open, two open-ended tube, all right? Now, the smallest wave that you can fit, which goes from, so if it's open, so the air molecule can vibrate as much as it wants, so to speak, right? So you're going to have like at both ends, you're going to have what is called an antinode, right? Antinode is a point of maximal displacement. Okay, well, of course, for longitudinal wave, it's going to be like this, right? By the way, here, this is not the motion of the air particles, okay? Because I cannot represent in a 2D page here like a longitudinal waves, because it moves like this. All right. So actually, the particles here are actually the air molecule are actually moving this way and that way. All right. And over here, they move a lot. Here, they don't move at all. It's just a node. Here, they move like just a little bit. All right. So it's a little bit less than that at both ends. And here, they move as much as they want here. Well, not as much as they want, but they have like as much displacement as they have in this particular case. All right. So the air molecules are moving this way. Right. So at one end, it moves like this, a little bit like further in, it moves a little bit like this. At the node, doesn't move. Past the node, moves a bit, and then so on. All right. So this is not a transverse wave. What is represented here is a transverse wave, but it's just to make it easy. Okay. So as I said, here you have two open end here. So you have an antinode. So an antinode right here, and then an antinode at the other end, and you have a node right in the center. So it's like going from a crest to a trough. Well, going from a crest to a trough is nothing else but half a wavelength. So you're fitting half a wavelength into the length of the tube. So you have a certain frequency associated with this. So this is the very first resonant mode that you can create. This is called the first resonant mode, also called the first harmonic. And this is also called the fundamental. Now, the second that you can fit is a full wavelength. So from a crest to a crest. So you're fitting a full wavelength in here. And the case is exactly, mathematically, is exactly the same as two closed end or two fixed end. So you're going to find out that the frequency of the second resonant mode is exactly twice that of the first. The third resonant mode, you're fitting like you're fitting 1.5 wavelength. So the frequency of the third resonant mode will be exactly 3 times that of the first, okay, and so on and so on. So it's exact, mathematically, it's the exact same description. And for that reason, for the reason that each successive mode are an integral multiple of the first, this is the reason why this is called a harmonic as well. So the first resonant mode is also called the first harmonic. It's also called the fundamental. The second resonant mode is called the second harmonic. It's also called the first overtone, and so on and so on. So the formulas here are exactly the same as the one above. All right. Okay, the last case is this one here. So if you can sort of find this in your notes here. So what we have here is a case of one that is closed, and at the other end, it's open. Okay. So this an example of this will be a closed air column. By the way, if I go back to this here, a two open end is also called a open air column. An air column, by definition, whenever you hear air column, I'll put this in the notes. Whenever you hear air column, it means it's open at one end by default. Usually, I'm a little bit more specific. I'm gonna say it's a 2 open end air column. It's a 1 open end, 1 closed end air column. So an air column is in the book is always open on one side. So an open air column means it's open on both sides, and a closed air column means that it's open on one side, but it's closed on the other side. Closed air column here. So an example of this would be like a steam whistle. The steam whistle is open at one end and closed at the other end. Now, what's the smallest portion of a wavelength you can fit into this? Well, it has to go from a node to a antinode. Well, this is nothing else but a quarter. So you're fitting a quarter of a wavelength. And then you're going to have a certain frequency. So it's called the first resonant mode. This is also called the fundamental, just as before. But now the next one here, it's not going to be like half. It's going to be like 3/4 of a wave. So you're fitting 3/4 of a wavelength into L, right? L is the length of the tubes or the trombones. And now if you do the calculation, remember here, the speed here is the same for all those modes, right? So the speed being the same, and so if you let like speed of 1 be equal to speed of 2, and then you put the wavelength in terms of L. So you're gonna find that for this case here, I'll put it like very quick here, but for this case, like this is gonna be like 4 times L, right? And then you do likewise here. What you're gonna do, what you're gonna find out, you're gonna find out the following. You're gonna find out that the second resonant mode is not twice that of the first, but it's actually 3 times of the first. It's not, and then the next resonant mode here, the third resonant mode here, you're fitting like 5/4 of a wavelength. And if you do the math, you're going to find out that the frequency of the third resonant mode is exactly 5 times that of the first. So the even multiple are not there anymore. Okay, and for that reason, this is why this is not called harmonics. You don't call harmonics. Okay, I think the textbooks sometimes give it wrong. They use harmonics for one closed end and one fixed end, but that's not true. Okay, so there's no harmonic. The first resonant mode is still called the fundamental. Second is still called the first overtone, and so on. But there's no more like first, second, and third, fourth harmonics. And it so happens that the ears seems to prefer like the even overtones. When the overtone is an even multiple of the fundamental. When they are an odd multiple of fundamental, it's not so pleasing to the ears. So that's why a steam whistle, well, it's not like it's not like extremely well pleasing to the ear, as you may note here. Yeah. So those instruments here that work with one closed end, one closed end, one fixed, one closed end, one open end, they're not very pleasing to the ears. So this one here is the formula here. So where N once again is the resonant mode. All right. So you're fitting here like a quarter wavelength, 3/4 wavelength, 5/4 wavelength, and so on. And you can see here, this is the formula for the frequency of the overtones in terms of the fundamental frequency. And you're going to get to n minus 1, you're going to get, of course, an odd number out of that. All right. So are you good for this? No questions? Yeah, there's a question here. All right, chat. Well, why don't you talk? Well, I mean, are you to memorize? Well, since you're not going to get like a quiz on this, I mean, you don't really have to memorize this. But if you were to have a quiz, a test, I would not sort of give you this on the formula sheet. It's not on the formula sheet, so you would need like to know that by heart. Okay, which is not that difficult to remember. Okay, madame. All right. So any other questions? Okay, so let's do a problem here together, and so let's do this. So this you can sort of put in your notes if you want. All right. So example. Okay. So a steam whistle has a length of let's say 3 meters. Fine. Okay, so there's the temperature, air temperature is, let's say it's a hot day like yesterday. Ooh, well, still today, a little bit less, but let's say it's 30 degrees Celsius. Okay, so A, fine. the fundamental frequency. Yep. Sorry. Frequency. Let me sort of put this. There we go. Find the fundamental frequency of the steam whistle. A lot of people decided to stay in bed today. All right, so find the fundamental frequency of the steam whistle. Okay, so the first thing you want to do is you want to ask yourself, is it a 2 open end, a 2 closed end, or 1 open end, 1 closed end? As I said earlier here, steam whistle is an example of a 1 open end, 1 closed end. One closed end. All right. So you can, if you want, you can. Let me use something a little bit nicer. There we go. There you go. Yeah, that's good. So what you can do is you can certainly sketch it. Sometimes I may ask you to sketch it. All right. So the fundamental. So once again, it has to be a node right here, and it has to be an empty node at this stage. So a crest or a trough. As we saw here, like the smallest portion of a wave you can put is a quarter wavelength, right? So what do we know? We know that L is equal to 3 meters. And here you're fitting a quarter of a wavelength. All right, so you're fitting a quarter of a wavelength into L. All right, so this is, you just write it as I say it. You're fitting a quarter of a wavelength into L. Of course, this is like L here. Right. By the way, it doesn't matter if the tube is curved. It doesn't really matter. So sometimes they call this the effective length, right? So you're going to get the same result here. All right, so from this one here, you can find here that the wavelength of the fundamental is going to be 4L. Yes, Max? Yeah. What? My mic is not okay, so yeah, kind of tight. Because I asked the fundamental, that's why. All right, so fundamental is the first resonant mode, Max. Okay, right. So remember here. So fundamental here. Right. So fundamental is always the first. Right. So first resonant mode always fundamental. Okay. All right. So let's go back. So what we have. Whoops. What we have is this. Now we want to find the frequency. Well, in order to find the frequency, of course, you're going to use this formula right here. Right? So where the frequency will be equal to speed over the wavelength. Now, this is a so what you're creating here, you're creating a standing mode, a resonant mode into air. Don't forget, again, like this is misleading. A standing mode doesn't mean that the wave doesn't move. It means like it's what you see is you see the overall result, right? You have like air sound wave consistently going this way and continuously being reflected back, right? Okay. Uh, so it has a speed, and the speed at which like sound travels in air, it depends on temperature. So that's why I gave the temperature here, right? So in order to find the speed, we need like the formula to find the speed of uh, of sound in air. So remember here, it's equal to 232, 231. Doesn't really matter which textbook you use here. And then for every 1 Celsius increase in temperature, the speed of sound increases by 0.6 meter per second, right? Right. So this is the formula here. If you want to use 231, doesn't really matter to me, all right? And we know what the temperature is. The temperature, all right, so if I put it here, the temperature is like 30 degrees Celsius, all right? I didn't put my givens here. I should have put my givens first, but yeah. All right, so you put this here. So 332 meter per second plus 0.6 meter per second per Celsius times 30 degrees Celsius. So the Celsius, of course, disappear. So 30 times, so it's 18, so 350. There we go. All right. So this is the speed of sound at a temperature of 30 degrees Celsius. Now that we have this, we can sort of put this into right here, right? So we'll do that. So F1 is equal to, so let's put this here again. So 350 meter per second over the wavelength, which is 4L. No, I didn't. So let me put the 4 length. So this was like 4 times 3 meter. So it was like 12 meter, right? So that was the, this is the wavelength of the fundamental. So we're 12 meter. All right, you're gonna have like 1 per second, which is nothing else but cycle per second, so hertz. So if I do this here, I get 12. So I get like 29, whoops. So I'm gonna get 29.17 hertz, which is pretty low. So that's the fundamental, right? That's very low. Very low. All right. You good? Okay, so let's do B here. Find the frequency the 12th overtone. So what you want to find the frequency of the 12th overtone. The first thing that you want to understand here is you understand the following here. You want to understand that the first is the fundamental. The second is the first overtone. The third is the second overtone. So you can see here that the number of overtone is, if you want to find like the resonant mode that correspond to this overtone, you just add 1, all right? So if you go back to this, 12 overtone means that it's going to be the 13th resonant mode. So what does it mean here? It means that n, this is my n here, is equal to 13, not 12. There you go, Justin. Goo just got up. I missed most of it anyway. Okay, and then what you do here, you don't, please don't try like to sketch it, because it's going to be like a little bit hard. Don't forget here that the length of the tube here stays the same here, right? So what you do is you make use of, yeah, it's a little bit laggy here. So what you do, you just make use of a formula right there. I'm giving you a formula that you would have to remember, Madhav. All right, so this is the frequency of the next resonant mode in terms of the fundamental, right? So this is exactly what we're going to use. So we're given here that Fn is equal to 2n minus 1 times F1. Here you want the 12th overtone, which is a 13 resonant mode. So it'll be like 2 times 13 minus 1. So I'll give you, was it 25? And then the 13 resonant mode will be 25 times that of the fundamental, all right? So if you do this here, times 25, so you get something like 529 hertz. All right, we good? So these are sample problems here. You can do. Good. Good morning, Justin. Just got up. There's another. Whoops! I don't know where it is. Is it here? No. Where is it? I think I forgot to. Pretty sure I put it somewhere. So let me describe. Is this here? No. Is it here? No. Here? No. Yeah, I wanted to sort of, I think I asked you, like, just give me a second here. All right, I'll just stop sharing it, and I'll sort of find what I want. Hope it's there. So let me see here. Ah, there we go. There you go. There you go. So this one here, I also ask you like to print it. I'm gonna wait. So if we're at school, I would have asked you like to actually like do this experiment, but you're not at school. What can we do? I wonder if next year I should sort of give you, you're supposed to do an IA. You've done only one lab. So you're not familiar with all the equipment I have. So I wonder if your IA, I'm going to ask you like to all do like data-based labs. It means like you don't actually like construct your experiment. You don't take data. Data is given to you, and then you work with it. I don't know. We'll find out. I even don't know if I'm going to have you in this in the fall or in the spring. So anyway, okay. So there's two ways here that you have to understand. So here I have like, so these are or one open end, one closed end. Okay. And if you're in class, I would sort of have like one open end, one closed end, or this is called a closed air column. So I would have closed air column of different length, and I can modify this length here. So what I would have like, don't write this down here. I would have like a water column here. So there's a column right here. There's water right there. Okay, and I would sort of make like the water go down, and as the water go down, I'm increasing the length of this open air column on the top. Okay, so this is what you would have. And then I would sort of have like a little tuning fork right in front of the air column, and this tuning fork here is of a set frequency of 512 hertz in this particular case. Now, if the water is up here, what happens here is that the speed of the air is fixed because it has a certain temperature in the room. And what happens here is this: if I have a frequency, this is the source here, right on top. This is the source. So if I'm creating like a 512 hertz. If I'm creating a 512 hertz, right, frequency here, and the speed of sound is fixed. Let's say it's 346 meters per second. It's not really important here. Okay, it's a room, right? What I want you to understand here, I want you to understand that the wavelength will be fixed. Wavelength will be fixed. So if the water were like this, I would not get resonance. There's no way I can get resonance because the wavelength is fixed. And probably for this distance here, this much distance here, it is not equal to a quarter wavelength. Remember, like for one open end, one closed end air column, the smallest you can fit is a quarter. So you would not have resonance here. You would hear like almost nothing. The tuning fork doesn't give off a lot of sound wave of very great amplitude, so it's not very loud to begin with. So if I put this over the air column here, you're not going to sort of hear much, and you're not going to have resonance. But the moment I lower the water up to a point, right? So this is the water here, up to a point where this is fulfilled. Now you're going to have like a quarter of wavelength. Don't forget here, the wavelength is fixed because my frequency is fixed and the speed is fixed. So wavelength is fixed. So when I let the water go down in such a way that the air column here is exactly a quarter of the wavelength determined like this, now you're going to have resonance in the tube. So you're going to have a standing wave in the tube. A standing wave has a great amplitude, and now you're going to be able to hear it. Okay, it will be very loud. Now, if I let the water go down even more, you're going to see this resonance disappear. All right, so let's see here. So let's say I'm right here. So the water is right here. Whoops. The level is right here. I have this air column. Well, I cannot have my second resonance here, right? Because it has to end with a node. So here it doesn't end with a node. So don't forget that the wavelength is indeed fixed, right? So the wavelength is fixed. So the wavelength is always fixed. So if I let like the water go down, at some point, I'm gonna sort of hear a second resonance, right? So when the water is that far down, so when the water level is that far down, now I have this air column right here, and now it fits the condition for resonance. It starts with an antinode and ends with a node, right? So I have a 3/4 of a wavelength, and you're gonna hear resonance again. And then if you keep on lowering the water level, there'll be a point at which you're going to hear resonance again. So if I let this go down, you're not going to hear resonance. So it's like here because it doesn't fulfill the 5/4 of a wavelength. And then at some point, whoops, 5/4 wavelength is realized here, right, in the air. So you'll have your third resonant length, third resonant mode here, okay? So don't forget, if the frequency is fixed, then the wavelength is fixed, okay? In contrast, if you want to keep this, air column here the same length, how do you get like another resonance? Well, you can get another resonance only by changing your frequency. All right. So once again here, so here I'm full. So there's a quarter wavelength into this much length here. I have a certain frequency here. Now, if I want to fit like 3/4 of a wavelength, if I'm fitting 3/4 of a wavelength here into the same length of the air column as over here, okay, I need to change the frequency, because you can sort of appreciate here, if I'm fitting 3/4 of a wavelength, of course the wavelength will be shorter, right? So you can see here, like this is half a wavelength here. This is a quarter of a wavelength, right? So I have to shorter the wavelength. How do I shorter the wavelength? Well, once again, the speed here will be fixed. This is going to be fixed. How can I shorter the wavelength? I can shorter the wavelength. So I want like the wavelength to go down. So once again, this is fixed here, right? This is fixed. So this one is fixed right here. So if I want the wavelength to go down, I need to increase the frequency. And this is exactly what I have here. So if I choose a tuning fork that is exactly 3 times that of this one, I'm going to create a resonance. Justin Gu again. I'm going to create a resonance right here, and it's going to be fitting like 3/4 of a wavelength here. Okay. So this is also called a second resonant length, even though it's, you see here, it's not the same length as this. But in this case here, you keep the frequency the same, and then you just increase your air column. In this case here, what you do is you change the frequency. Don't forget, V is always fixed. You change the frequency in such a way as to fit in the same air column here to fit like a wavelength of shorter wavelength, all right? And then if I want to fit 5/4 of a wavelength, then I have to increase the frequency by 5 times, all right, and so on. Is that okay? All right, so this is a two-way of looking at resonance here. So just Justin, I think the screen share is glitching out on me. I don't see anything but a black screen. Well, that's what happened. We come in late. I'm going to rejoin and see if it fixes the problem. Does it fix the problems, Justin? I hope so. Okay, so any question for this? All right. The last thing I'm going to talk about here is richness of a sound. So richness of sound. So if you play a C note on a piano, a C note on a trumpet, a C note on the same note on a guitar, you know how to tell those instruments from each other. How can you do this even though you play the same note? Well, you can distinguish them because like each instrument will give off a certain amount of different amount of overtones. All right, so a sound is said to be rich, is said to be rich when it contains a lot of overtones. No, lots of overtones. So for those who were there, like last day before the March break, I tested your hearing. I tested like how until what frequency, what frequencies you can hear and what frequencies you can no longer hear. You remember that? And remember that those sounds were not very pleasing. This is a pure sound. I'm outputting a pure sound. There's no overtones, and it's kind of annoying. But if I were to sort of put like more overtones on it, then it would be pleasing. Okay. So a sound is said to be rich when it contains lots of overtones. So what happens here is that if this is your fundamental, so this is your fundamental, and then you have like a lot of let's say overtones here. All right, so first overtone. All right, so let's say here, I don't know. There you go. So third overtone. All right, and so on. Uh, what are you going to create here? You're going to create a sound. So you can see, well, let me sort of do it like a little bit better here. So you get the shape, you get the general shape of the fundamental, and you have those little peaks because I've been like adding them using use using principle of superposition here. There you go. All right, so this is a rich sound, right? This is not super rich. There's only two overtones here, but it's richer, right? It's a richer sound here. And then you're going to still perceive it as the fundamental frequency. All right. So if this is like a 500 hertz, you're still going to be perceive this as a 500 hertz, but it's going to be richer. It's going to be more pleasing to the ears. Although I've put like odd overtones, so probably it's not going to be as pleasing if I were to put like even overtones. All right. Yeah. So this one here is not rich. Okay, it's annoying. Okay. And the reason why, once again, if you play a C note on a guitar versus a C note trumpet, the fundamental in both cases, will be the same, right? So if you play the same note, the C note, let's say like 256 hertz on the guitar and 256 hertz on the trumpet, you're going to perceive the same frequency, the same pitch. You're going to tell them apart because perhaps the guitar will have the first overtone, but we'll be missing the third overtone. All right. Whereas the trumpet may not have the first overtone, but may have the third overtone. And this is how you're going to sort of be able to tell them apart. Wow, look, this is like I told you yesterday. It was at 9:45. Anyway, all right. So this is how you can tell the different instruments apart, even though you play the same notes, because different instrument will allow different amount of overtones with different intensity. All right, so questions? Well, that's it, guys. I'm done. I'm done. Um, so as I said, so tomorrow it should be visible. Like if someone like can test this on D2L, if you can sort of go, I should have put like the sound ISU. Oh, actually, I'm stupid. I put like turn it in. I don't want turn it in. Okay, don't submit yet. I have to change this. Okay, I don't know why I put turn it in. Okay, I'll remove turn it in. All right, so don't put it yet. Just give me a second here. Just I will sort of fix this. Uh, but it should be there. So once again, make sure that you take, I want it like not an image, I want it to be a PDF file. So your image, make sure that your images are changed into PDF file. And then use a software, whatever, like if you have a software that allows you to combine them, or use the software that I put on the website. I prefer the software that I put on the website because the other ones very often it's online. So what you put, you give this to whatever company it is, right? So when you put this online, it's the possession of whoever owns the software, right? So I don't like this. So the software I put on the website here is the one that you can download, you can install on your computer, and no one will ever see those PDF files, right? So can you go back to share? Yeah, I will just a second, Max. Okay. So so make sure that this is make sure you put like one file, one big file, one PDF file. Make sure they're in order. and then include also the cover page. And you have to send this in by 4:30 tomorrow, so Thursday. Do not wait until 4:30, guys. Okay, 4:30. Like if you start like, okay, I'm gonna start at 4:29. No, so make sure that you do this before. You can combine PDF directly by dragging, dropping the preview app on the Mac. Yeah, so I know, like, yeah, a Mac is good. Mac is good. So yeah, so far it says like if you have like a preview, if you have a Mac, you have preview, can drag and drop them. And I didn't know that it combines them, but that's good. So yeah, you can make sure that they are in order. Okay, so let me sort of see here. Can someone tell me if you can see it on D2L? I will sort of change it, but you go on D2. Can you see it?
Yeah.
Yeah. Yeah. Okay. Let me sort of change. Oh, some people have already. Natalie is quick. Okay. All right. She's already put the assignment there. Okay. Let me sort of get rid of. Why did I put Turnitin? Idiot. Okay. Ding. There you go. No Turnitin. There we go. Okay. So it should be good to go. Save success. Yeah. And I can see name is required. What do you mean name is required? I did give a name. What's that? It's newest. I don't want to do a new assignment. Hold on a second. Cancel this. Let me go back to, okay, Sound ASU. Okay, edit assignment. I know I'm talking to myself. Hold on a second. Turn it in. Do not put turn it in. Yeah, it's okay. It's fine. Okay, save as close. Yeah. Yeah, so it's alive, so you can put it in. So I can see Natalie and Timothy already did. All right, and yeah, so make sure that this is done by 4:30. Okay, tomorrow. All right, Tuesday. So next Tuesday. So next Tuesday at 10 o'clock, we'll meet again, everyone, and I'm gonna start talking about your CPT. Okay, so once again, next Tuesday, so that will be June the 2nd. So June the 2nd at 10 o'clock. So make sure that everyone is there, and I will explain your CPT. All right. Okay, any questions? All right. Okay, so as I said, we're done with the, yes, Madhav.
Are we not meeting tomorrow?
No. No. The next time we're going to meet is on Tuesday, and that's it. We're not going to meet again. Well, until I see you hopefully next year. All right, because I'm done. I'm done with everything. As I said, I'm going to explain the CPT on Tuesday. You're going to work on this, and why? I don't know. What will we use as a cover page? It's the cover page for the ISU is the page that I gave you, like which problems you have to do and all this. That's where it is, Luke. Okay, try to find it, or just ask someone else to email the cover page if you need. All right. Okay, guys. So I wish you like a very nice weekend here. I think it's gonna be hot. So make sure that you drop like this Sound ISU by tomorrow by 4:30, and then I'll see you like again on Tuesday, next Tuesday at 10 o'clock. All right, 10 o'clock, not 10:30, but 10 o'clock. All right. All right, guys. So God bless and see you soon. Bye-bye.